আচ্ছা, স্ক্রিন দেখতে পাচ্ছ সবাই?
হ্যাঁ ম্যাম।
Okay. Okay, so we'll start from here. আগের অতটা okay. So in our last class and the class previous to that, we had started our discussion on the quest of a wave that could represent a moving particle in compatibility with the complementarity principle, which says that if energy is dual, so must be matter. And then deBroglie gave his hypothesis, which said that every moving particle has a wave associated with it. And then 3 years after deBroglie gave his hypothesis, people started designing experiments to actually look for this wave associated with a moving particle. And as you know, Davison and Germer were the first people to see a phenomena in when they impinged electrons on a crystal which has a homogeneous atomic structure, and the interatomic space is of the order of a few angstroms. And they saw that the electrons that if you consider electrons to be particles, so the electrons that sort of reflected from these atoms of the crystals, when they were detected, they showed a result which could not be explained by their particle behavior. The peak at a particular value of voltage and a particular value of the angle of the detector that was observed would only be possible if something like a constructive interference was taking place. And we know that a constructive interference kind of thing can take place only for waves. So they did some calculations and they saw that using Bragg's law, the value of the wave that could result in such a peak came to be exactly same as the value of the deBroglie formula for the given electron. Okay, so this was the first experimental establishment of the presence of a wave associated with the particle. And then of course later on Thomson and others, Stern and Gerlach, they did similar experiments. And all these, so neutron diffraction showed Laue patterns, and hydrogen atoms and helium atoms showed diffraction, which again showed Laue patterns. So all these formally established the hypothesis that deBroglie gave, and finally deBroglie of course got a Nobel Prize for his hypothesis. Now the next, so now that we know that yes, waves are associated with moving particles, and just like energy has dual characters, so does matter. They sometimes show particle characters and sometimes they show wave characters. Now the next question that comes is the nature of these waves. If these waves are associated with the moving particles, uh, what are they like? Are they monochromatic waves, the plain progressive waves that we use to represent electromagnetic waves? Are they the same, or they are some other kind? Okay, so that was the next level of search that people started doing. So for this, let us look at the properties of matter waves. So this is the velocity of the wave, right? V wave equal to nu lambda. Both these are not V. This is V and this is frequency nu. So all of you know this formula from your high school physics classes. And from this we can say that the deBroglie wave associated with a moving object can be written as E by P. All right. So if we consider non-relativistic motion of a particle, then This value, we take non-relativistic energy of the moving particle, which is half mv square, and momentum is mv. Then the value of this velocity, the velocity of the wave associated with the particle, comes to be v by 2, where v is the velocity of the particle and vw is the velocity of the wave associated with the particle. Now this is very absurd, because the wave that represents the particle seems to lag behind. It has half the velocity. It is moving with half the speed of that the particle is moving. So if the particle moves with, say, 1000 kilometers per second speed, the wave would move with a 500 kilometers per second speed, which is absurd. Like it's like a trail. It will be trailing the particle at all points of time. Then if this would happen, then the experimental observations could not be true. So where did we go wrong? That we have to find. So a simple monochromatic sinusoidal wave, we all know, is represented by this function, and we know that for a given x, this is an oscillatory function. It oscillates sinusoidally with time, with frequency mu. Also, for a given t, the function has a sinusoidal dependence on x with the wavelength lambda. And the nodes of these functions are present at the positions where 2 pi kappa x minus mu t becomes, takes the value of n pi, n equal to 0, 1, plus minus 1, plus minus 2, etc. So if you consider the movement of such a node, then you'll see that the node will be moving with a velocity v omega, vw, that is velocity of the wave. So obviously so it is not moving with a velocity v by 2. Okay, so this kind of a monochromatic wave cannot be the matter wave that we are looking for. We must think in a different way. We must change the direction of our thinking, and only then will we find the actual nature of the wave that is associated with a moving particle. Okay, so I remember describing this thought experiment to you. So we think of an experiment. This experiment is not practically possible, but we can think of performing such an experiment where, suppose, this red dot is my moving particle. Okay, and what I do is I keep several instruments along the path of travel of the particle. So the particle is, say, moving in a certain direction, and all along its path on both sides I keep instruments. Okay, and what do these instruments do? They measure the amplitude of the wave that is moving along with the particle. Okay, you can imagine that we have designed such an instrument which is capable of measuring the amplitude of the wave associated with the moving particle. So these instruments that I have kept along the path of the moving particle does that. So if you think logically, then the observation of these instruments will give us a plot like this. Because at any instant of time, the particle can be present at any one place. So it's highly localized. So the amplitude will have a very high value in the vicinity of the particle, and it will gradually decrease to 0 as the wave moves away from the particle. Okay, so we cannot possibly have a wave which will move with undiminished amplitude for eternity. That cannot possibly represent a particle which is actually physically existing. So the wave, such a wave has a modulated amplitude, as you can see, and we know that it has, and as I told you, that it has non-zero value only in the vicinity of the particle that it is representing. So we can say that a matter wave will be a group of waves, not a single monochromatic wave, but a group of waves that is moving along with the particle with the same velocity. Alright, so we must consider adding a group of waves where the number of waves are infinite and they are all moving in the same directions, and all of them have infinitesimally differing values of frequency and wavelength or reciprocal wavelength kappa. Okay, so this is what our intuition is telling us. In order that the wave represents a moving particle, we must have something like this, which is clearly a wave with a modulated amplitude, and a wave with a modulated amplitude is obtained only there if there is a superposition. If you can recall your sound wave chapter where you derive the expression of beats, remember, when two waves are moving in the same direction and have slightly different frequency and wavelength, then you got something like this, waxing and waning of the sound. So something like that should be happening over here. Okay, now fortunately, right at this moment, we don't have to add up infinite number of waves. We will do the mathematics for addition of two waves, and we'll get a result that will show that addition of two waves itself gives a result close to this, so that when we increase the number of waves gradually to infinity, then we will get exactly this result that we have intuitively arrived at. Okay, before that, let us talk a bit about group velocity and phase velocity of waves. We have been talking about groups of waves, and before that we had been talking about monochromatic, single monochromatic waves. So before proceeding to adding up and getting the result that we want, let us have a short discussion on what are the terms, the group velocity and phase velocity. Okay, now once again, a plain simple harmonic in the positive x direction is given by this equation, and as you can see, the phase of this function psi is also a function of x and t, right? The phase is given by this function, and it is, I represent it by the function phi xt omega t minus x pi. So differentiating this with respect to t, you get del phi del t is this omega 1 minus 1 by 2 dx dt. What do we get? If we want a point of constant phase, when the wave is moving forward, when a simple harmonic, plain simple harmonic wave is moving forward, if you look at a particular point of the wave that has a constant phase, then the phase of course does not change with time, so del phi del t is 0, and that gives us dx dt equal to v. Alright, so the point of constant phase moves forward with a velocity v, which is the which is called the phase velocity. Okay, because v is the velocity with which the point of constant phase moves forward. This is known as the phase velocity Vp of the wave. So basically, the phase of the single simple harmonic wave moves forward with a velocity Vp. Alright. Now, if you replace V by Vp in the wave expression, then this is what we get. Psi is A sine omega t minus kappa x, where we have used kappa equal to omega by Vp, or kappa is 2 pi by lambda, and we know by now that kappa is variously known as the propagation constant or the wave number or the reciprocal wavelength, because at several places instead of the wavelength itself, we use the value of the reciprocal wavelength 2 pi by lambda or kappa. Okay, and as you know, a sine omega t minus kappa x is a familiar expression of a plane progressive wave. We already got the phase velocity as omega by kappa. Vp is omega by kappa. So at this point of time, we will come across two new terms. One is that while traveling in a medium, if the phase velocity of a wave varies with the wavelength or frequency of the wave, we call that medium a dispersive medium. Once again, if while moving through a medium, the phase velocity varies with the wavelength or frequency of the wave, we call it a dispersive medium. You all know a prism is a dispersive medium. When light, an electromagnetic wave, enters the prism, the different wavelengths start moving with different velocities, and on the other side we get the component colors of white light. Alright, so this is what I mean by a dispersive medium. On the other hand, if the phase velocity does not vary with the wavelength or frequency, the non-dispersive medium. Just like when light moves through air, it does not split up into its component color. So air is a non-dispersive medium for light, for an electromagnetic wave. Okay, why we required these terms, you'll come to know in a while. So when several plane waves of different wavelengths, we just saw when a single wave moves, then the point of constant phase moves ahead with a velocity known as the phase velocity, and its value is given by the ratio of omega and kappa, angular frequency and reciprocal wave. Alright. Now if you consider several such plane waves which has different wavelengths, if they travel simultaneously in the same direction through a dispersive medium, what will happen? They will superpose on each other, right? And the result is a formation where we get groups of waves. And each such group will travel with a velocity Vg, which is called the group velocity. I'll show you a picture in a moment which will make this thing clear, the concept will be made clear. For the time being, just understand that we are considering several such, this plane wave is one single wave. We consider several such waves all moving side by side, or let us say one on top of the other in the same direction. But they have different wavelengths. They don't have same wavelengths. Okay. So what will happen, it can be mathematically shown that they will superpose on each other and they will produce a resultant function which will consist of groups of waves, and each such group will travel with the velocity Vg, called the group velocity, and we'll soon see that this group velocity is completely different from the phase velocity of the single wave. Alright. Now let us do the mathematics of superposition of two waves traveling in the same direction. And this again you have all done with beats in your sound chapter, where you did the superposition of two waves traveling in the same direction. Remember, when two waves travel in opposite directions, they fall on each other to form stationary waves. That is a different thing. Here we are talking about two waves traveling in the same direction. So they will be propagating. They will not form stationary waves. They will be propagating in the direction that we are talking about. Alright. So let us represent wave 1 by the function psi1 xt, sine kappa x minus omega t, and wave 2 is given by psi2 xt, which has a wavelength that differs from wave 1 only slightly. So wave 2 has a wave number kappa plus d kappa and a frequency omega plus d omega. Okay, so the frequency and wavelength of the second wave varies only infinitesimally from the frequency and wavelength of the first wave. So as you know, the resultant wave will be obtained by the addition of psi1 and psi2. So if you do this little bit of trigonometry, the result that you get is this, where of course I use the formula sin A plus sin B equal to 2 cos A minus B by 2 sin A plus B by 2. So what do we get over here? We get two terms, the resultant wave, which is formed by the superposition of the two waves with infinitesimally varying frequency and wavelength and traveling in the same direction. I'm repeating this several times, consists of a product of two terms. Okay, and if we simplify this, then we can write psi equal to 2 cos dk by 2x minus d omega by 2t sine kappa x minus omega t, where we have considered the fact that since dk and d omega are infinitesimal changes, so obviously twice k is much more than dk and twice omega is much more than d omega, so that in the sine term we neglect dk and d omega with respect to twice k and twice omega. So what we get is sine kappa x minus omega t, and we have this term here, the term in front, the cosine term. As you can see, this sine term is the same as the function in 1. So the sine term of the resultant wave does not change. This is the actual wave that is moving forward, right? It is the same as the function in equation 1, which is representing a plane wave moving in the positive x direction. However, now we have this second term, which is the cosine term and which modulates the sine term. Okay, so the sine term remains the same as in equation 1, but it is modulated by this first term, which is the cosine term. All right, and therefore the propagating wave is enveloped by the periodically varying amplitude. Can you see that the wave propagates with in the same manner as the original wave, but it now has an envelope which also varies periodically. So the amplitude is no longer constant. We now have an amplitude which itself varies periodically, which itself is a cosine function. Which means that when two waves move together in the same direction and when they have infinitesimally differing wavelength and frequency, then they form a group which, as you can see from equation 4, moves in the same direction as the individual wave as directed by the sine term, but which has a modulated amplitude which itself is a periodic function. Is this clear to everybody? This slide is very, very important. It's very simple mathematics, but it is very important for you to understand how the group is produced. Is it clear to you, or do you want me to explain anything, repeat anything once more? I'm sharing screen and I'm on my PPT page, so I can't see anything. Someone please unmute and say whether you want repetition or can I move to the next slide? Should I go to the next slide?
Yes, ma'am. Okay.
Okay. Okay. So, from the expression, from the mathematics of two waves, we see how a group is generated. All right. Now, velocity of propagation of the individual waves is of course obtained from the sine term, right? Because each wave moves governed by the sine term. So it is again omega by kappa, the phase velocity. Velocity of propagation of the envelope or the group, that will be obtained by the amplitude term, because the amplitude now is a periodic function. So if we our previous slide, we see that velocity of propagation of the individual waves is still omega by kappa, but velocity of propagation of the group is governed by the amplitude, and the velocity will be given by d omega by 2 by dk, or d omega. So that is the velocity of the group, or the group velocity. Okay. Now we saw that the amplitude of the resultant wave is this 2 cos dk by 2x minus d omega by 2t, and therefore we can write the group velocity is equal to d omega dk. But from our previous knowledge of Einstein and Planck and deBroglie, we know that E is h nu, which can be written as h cut omega, and P is, the momentum is h cut k. So we can write Vg as d omega dk. We multiply h on top and bottom, and we get Vg equal to de dp. So the expression of the group velocity is de dp, or d omega dk. So you can see that whereas the expression of the phase velocity is simply omega by kappa, the expression of the group velocity is d omega d kappa, or de dp. Now for a non-relativistic motion, we have E as half mv square and P as mv, so that if you find the expression of Vg, for dE you can write mv dv, and for dp you can write mdv, and the value comes out to be v, which is the velocity of the particle. Okay. So whereas when we try to get the velocity using the phase velocity expression, we saw that the velocity is coming out to be half of the velocity of the particle, which showed that it cannot represent the wave related to the particle. But if you take into consideration more than one wave, in this case, the simplest case, we take two waves and we see that they superpose to form a group, and we can see even in this simplest case that the velocity of the group, the velocity with which this group moves forward, Vg, is its magnitude is the same as the value of the velocity of the particle. Okay. So this is what I am talking about. I have given the mathematics for the addition of two waves, and in the picture I've used the addition of three waves. So as you can see, we have three waves here. They have equal amplitude, but they are slightly different in their wavelength and frequency, right? This has higher frequency than this, and this has higher frequency than this, and the wavelength is greatest here and it gradually decreases. So these three waves, they are propagating in the same direction with the velocity Vp, but they have slightly varying wavelength and frequency. But when they do propagate along the same straight line, they superpose, and what they produce is a disturbance like this. So the envelope, the wave is still moving forward with the velocity Vp, the individual waves, but the envelope now is modulated by the periodically varying amplitude function, and the envelope or the individual groups are now moving forward with the velocity v, which is the velocity of propagation of the particle itself. Okay, is the picture clear to you? Have you understood? Because so long I was just telling you what was happening, describing. Now I have shown you the picture, what exactly happens when I make three such waves or more than one such wave superpose on each other. Okay, so as you can see that here we are getting something, the envelopes or the groups that are moving forward, they are similar to the, just a second. Yes. So remember this.
ম্যাম
Yes. হ্যাঁ বলো।
ম্যাম বলছিলাম ওইটা তো মানে আমরা এখানে তিনটে ওয়েভ নিয়ে করেছি, এটা তো মানে যেখানে পড়ছিলাম সেখানে তোমার মানে সেখানে করে করেছে ওই ফুরিয়ার ট্রান্সফর্ম ইন 2D
হ্যাঁ
স্পেস।
আসছি, দাঁড়াও 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 আসছি। প্রথমেই
ম্যাম
ফুরিয়ার
আমি বলছি,
ট্রান্সফর্ম করে দিলে হবে?
ম্যাম আমি বলছি সাইন ওয়েভের জায়গায় মানে ওটা কি আমরা জাস্ট ওই এক্সপোনেনশিয়াল ফর্মে রাখতে পারি?
হ্যাঁ নো প্রবলেম, তোমার ওয়েভটা চাই, ওয়েভ ফর্মে রাখলেই হলো। অঙ্কটা তো তুমি যেভাবে করবে তোমার তোমার রেজাল্টটা এক হলেই হলো। Okay, so this is what we had anticipated logically, that if something were to represent a moving particle, then it should be something like this. This was our intuitive anticipation from the thought experiment. Now we have shown mathematically that that is the case. Okay, mathematically we have seen that it is such a wave. So if the particle moves forward in this direction, I still I'm very sorry, I still have not been able to learn animation. uh, if I could make some GIF images for these slides, it would be better for you. But there are several images available on the internet. You can always go back and you can go and check for these, you know, moving images, which I am unable to make, unfortunately. So if the particle you considered move like this, then what moves along with it is this group, okay, with the same velocity as the particle. I hope all of you can picture what I'm trying to say. Okay, so this is
ম্যাম,
the, yes, bolo.
ইচ ওয়েভ যে স্পিডে যাচ্ছে তাদের গ্রুপটাও সেম স্পিডে যাবে?
না, না তো, ওয়েভটা যখন আলাদা যাচ্ছে ও তখন ফেজ ভেলোসিটি নিয়ে যাচ্ছে ওমেগা বাই কে, কিন্তু আমরা তো দেখলাম যে
হ্যাঁ,
ওমেগা বাই কে স্পিডটা ওই একটা আলাদা, মানে একা একটা সিঙ্গেল ওয়েভকে যদি আমি পার্টিকেলটাকে রিপ্রেজেন্ট করতে দিই, তাহলে পার্টিকেলের ভেলোসিটির থেকে ওর ভেলোসিটিটা অনেক কম, হাফ, সুতরাং তো হতে পারে না। কিন্তু আমি যদি ভাবি যে একটা পার্টিকেল যখন এগোচ্ছে তখন ওর সাথে একটা ওয়েভ নয়, অনেকগুলো ওয়েভ একসাথে এগোচ্ছে, ইচ ওয়েভ উইথ দ্য ভেলোসিটি ভিপি, মানে সবারই ফেজ ভেলোসিটিটা ভিপি, কিন্তু তাদের ফ্রিকোয়েন্সি আর সরি ওয়েভলেন্থ গুলো ইনফাইনাইটেসিমালি ডিফার করছে ফ্রম ইচ আদার। তাহলে কি হবে? এরা যখন একসাথে যাচ্ছে, এরা তো একজন আরেকজনের ঘাড়ের ওপর চেপে যাচ্ছে, ঠিক আছে, আলাদা আলাদা তিনটে লাইন না, কিন্তু মানে আমি ছবিতে তো ঘাড়ের ওপর দেখাতে পারছি না, এরকম তিনটে আলাদা লাইন কিন্তু নয়। যে অ্যাডিশন দেখাচ্ছি, অ্যাডিশন মানে অ্যাট দ্য সেম টাইম, সাইমালটেনিয়াস, তার মানে হচ্ছে এর ওপরে এর তার ওপরে তিনজনের ঘাড়ের ওপর চেপে যাচ্ছে। যখন ঘাড়ের ওপর চেপে যাচ্ছে তখন ওদের তো ইন্ডিভিজুয়াল আইডেন্টিটি আর থাকলো না, তখন ফেজটা স্টিল মুভ করছে ওই ভিপি স্পিডে, কিন্তু ওর অ্যাম্পলিটিউডটা মডুলেটেড হয়ে যাচ্ছে। এবার তুমি কি দেখতে পাবে? তুমি তো অ্যাম্পলিটিউডের প্রপাগেশনই দেখতে পাবে, কারণ তুমি তো দেখবে ইন্টেন্সিটি তো অ্যাম্পলিটিউড স্কোয়ার। তো অ্যাম্পলিটিউডটা প্রপাগেট করছে উইথ ভেলোসিটি ভিজি। এবং দেখো, নন রিলেটিভিস্টিক ক্যালকুলেশন যদি তুমি করো তাহলে তুমি দেখতে পাবে যে ভিজির ভ্যালুটা মানে কোয়ান্টিটেটিভলি ম্যাগনিটিউড অনুযায়ী ইজ দ্য সেম অ্যাজ দ্য ভেলোসিটি অফ প্রপাগেশন অফ দ্য পার্টিকেল, যেটা নিয়ে আমি শুরু করেছি। তার মানে পার্টিকেল যখন মুভ করছে ওর সাথে সাথে এই ওয়েভ প্যাকেটগুলো মুভ করছে। বোঝাতে পারলাম?
হ্যাঁ ম্যাম।
ওকে, okay, excuse me, just drinking some water. All right. This is a very very important concept, and আমার মতে, যদিও আমার মত কেউ নেবে না, কিন্তু আমার মতে এই জিনিসটা তো শর্ডিঞ্জার ইকুয়েশন শেখার আগে এই জিনিসটা শেখা উচিত ছিল, তারপরে শর্ডিঞ্জার ইকুয়েশন শেখা উচিত। কিন্তু তোমরা তো শর্ডিঞ্জার ইকুয়েশনের প্রচুর অঙ্ক আগে করে ফেলেছো, বাট ঠিক আছে, মানে শেখা তো হচ্ছে, শেখা হলেই হলো আর কি, জানা থাকলেই হলো। Now we will find out a relation between the group velocity and the phase velocity. হ্যাঁ বলো।
ম্যাম বলছি মডার্ন মানে আগের বার মানে সেমিস্টার 4 এর প্রথমে তো এইগুলো সব ছিল, মানে ফেজ ভেলোসিটি, গ্রুপ ভেলোসিটি, ইয়ে
হ্যাঁ,
এক্সপেরিমেন্ট।
ডাভিসন-জার্মান এক্সপেরিমেন্ট, এখন সেটা নেই, কিন্তু এই ক্যারেক্টারিস্টিক্স অফ ম্যাটার ওয়েভ এই ফর্মে কি ছিল? ওটা ফুরিয়ার ট্রান্সফর্ম কি ছিল?
হ্যাঁ ম্যাম, মানে ওই যে আপনার যে মানে আপনি তো ওই পস্টুলেট থেকে স্টার্ট করিয়েছেন,
হ্যাঁ,
পস্টুলেটের আগে একটা মডিউল আছে, ওই মডিউলটাই সবকিছুই ছিল, এই গ্রুপ ভেলোসিটি, ফেজ ভেলোসিটি, তারপরে ওই এই এক্সপেরিমেন্টটা কি নাম, কম্পটন, মানে পুরো ওটা সবটাই আছে
হ্যাঁ,
ওখানটায়।
কমপ্লেন ওগুলো তো ছিল আমি জানি। যাই হোক, এটা তো আছে, মানে এখনো আছে, তুমি যদি সিলেবাসটা দেখো তাহলে এখনো তোমাদের শুরুটা হচ্ছে এইটা দিয়ে, যেখানে ক্যারেক্টারিস্টিক্স অফ ম্যাটার ওয়েভস দিয়েই সিলেবাসটা শুরু হচ্ছে। আচ্ছা, the relation between group velocity and phase velocity, let us see. This is a very very easy calculation. We know the wave number is given by this, and phase velocity definition we got, it is omega by kappa, or omega is vp kappa, and group velocity we just now find out is d omega dk. So now if you replace omega by vp kappa here, you will see that phase velocity is group velocity is vp plus kappa dvp d lambda dk. And if you find an expression for d lambda d kappa, it comes out to be minus 2 pi by kappa square, which shows that vg, the group velocity, is bp minus 2 kappa dv d lambda. Okay, so this is the relation between the group velocity and the phase velocity of a group of waves that are
ম্যাম
moving forward.
আপনার নেটওয়ার্কে মনে হচ্ছে কোনো একটা প্রবলেম হচ্ছে, মানে প্রচন্ড আওয়াজটা আপনার ওই মডিউলেটেড আসছে, কেটে কেটে কেটে, মানে মানে কেমন রোবোটিক মতো।
আমার নেটওয়ার্কে আমি তো এইটাই ইউজ করি সবসময়, মানে সবারই কি তাই একই প্রবলেম হচ্ছে?
এখন ঠিক হয়ে গেছে, এখন ঠিক হয়ে গেছে।
আচ্ছা, তাহলে হতে পারে আমার আমি ইয়ারফোন ইউজ করছি তো মাইক্রোফোনটা ঝুলে আছে, হয়তো আমি মাথা নাড়ছি কাছে তো ওটা নড়ছে। ঠিক আছে, আমি ধরে আছি মাইক্রোফোন। Okay, so this is the relation between group velocity and phase velocity. For a dispersive medium, we just defined dispersive medium in a previous slide. So for a dispersive medium, dvp d lambda is a positive value because phase velocity differs with wavelength in a dispersive medium, and in that case the group velocity will be lesser than the phase velocity. However, for a non-dispersive medium, this does not make any difference. For a non-dispersive medium, the group velocity and the phase velocity will have the same value. Alright. Now, what is the size of such a wave packet? The wave packet that we saw in this slide here, these wave packets, what is the extent or the size of such a wave packet? And this is very important. This is a very important quantity. Why, you'll soon come to know. So if you consider two successive positions, x1 and x2, on the propagating group of waves where the amplitude is 0, okay, so the beginning and end of a wave packet we are considering, then from the expression of the amplitude we can write this, and it will be 0 at 2n plus 1 pi by 2. So 1 is this at x1 and the other is this at x2. Okay, of course we are considering x2 greater than x1 because we are moving forward in x. So subtracting, we would get x1 minus x2 is equal to 2 pi by d kappa. Alright. Since kappa is 2 pi by lambda, so d kappa is minus 1 by lambda square 2 pi d lambda, which means that x1 minus x2 is this value, so that x2 minus x1 is lambda squared by d lambda. Okay, so the length of a wave packet that we have just now encountered has this value, lambda squared by d lambda. So how large the wave packet, how large or how small a particular wave packet will be is entirely decided by the wavelength and the difference in wavelength of the constituent waves of the group. Alright. However, this is of course an estimated or approximate value because we have considered only two waves in this case. Alright. Now, before moving over to the final portion, let us see what is the phase velocity of deBroglie waves. Alright. We have already seen that the expression for deBroglie wave is omega by kappa. So, and we also know that the expression for momentum and energy are h cross kappa and h cross omega. So E by P is omega by k, which means phase velocity is E by P. Now, if you take relativistic consideration, then total energy is mc square and momentum is mv, where m is the relativistic mass, and then Vp becomes equal to c square by v, which is greater than c, the velocity of light. Now, this of course is an absurd result, right? It is not possible relativistically. Any velocity greater than the velocity of light is not possible relativistically. Which means that such a velocity of a moving particle has no physical meaning. This is my argument, like I am giving you more argument in support of the fact that a single monochromatic wave cannot represent a particle. Because if it did represent a particle, then its velocity would have been Vp, and then that would have been greater than the velocity of light, which is an absurd result, relativistically impossible for a moving particle, and it would not have any physical meaning. So therefore, once again, we conclude that we must associate a group of waves resulting in the formation of wave packets with moving particles instead of isolated monochromatic waves. Okay. Now, these discussions that we have done so far, let us jot down the nature of the deBroglie waves, that is the nature of the matter waves, after which we will finally see what the actual mathematical expression for a matter wave is. Now, what is the nature of the deBroglie waves? First of all, since a monochromatic wave is of infinite extent, it cannot represent a material particle. Okay? Secondly, for a monochromatic deBroglie wave, the phase velocity becomes greater than c, so a moving particle cannot be represented by such a wave. Then at any given instant, this is very important, you have to understand, or you have to keep in mind, that at any given instant the presence of a particle in motion is highly localized, even if it is moving with a very high velocity. At a given point in time, if you consider an instantaneous moment, then at that moment the particle is highly localized in space. Therefore, such a particle has to be represented by a wave packet. Now, if lambda is the wavelength of the deBroglie wave associated with the particle, the superposition of a number of waves which have wavelengths which are infinitesimally different from lambda and which travel along the same straight line will generate the groups of waves with modulated amplitude, and these are what we call the wave packets. And as we saw in the picture where I showed you the superposition of three such waves, the amplitude of each such packet varies from 0 to a maximum and then back to 0, and the dimension over which this variation takes place, 0 to maximum to 0, is the dimension of the concerned particle. Which is why I told you the calculation of the size of the wave packet is very important. Okay, so the wavelength associated with the wave packet or the moving particle becomes very important, because that gives you the size of the wave packet, and the size of the wave packet must be of the order of the dimension of the concerned particle, because it is only then that it can represent the concerned particle. Okay, so obviously it is logical to associate such a wave packet with a moving particle, which,
ম্যাম
yes,
ম্যাম
bolo.
লাস্ট পয়েন্ট বলবেন ওই ডাইমেনশনটা মানে কি করে অ্যাসোসিয়েট করছি, মানে একটা পার্টিকেলের রেডিয়াস ধরুন অফ দ্য অর্ডার 10⁻⁻6 সেন্টিমিটার, তো ওয়েভ প্যাকেটের ডাইমেনশনটা কতটা কেমন হবে?
ওই রকমই হবে, ওই
মানে ওইটা
অর্ডারের হবে,
হাইয়েস্ট অ্যাম্পলিটিউড হবে।
ওই অর্ডারের হবে, কারণ পার্টিকেলটা ওই ওয়েভ প্যাকেটটা বেসিক্যালি তো তোমার হচ্ছে ওর আনসার্টেনটি প্রিন্সিপালের ডেল্টা এক্স,
হ্যাঁ
তাই না? তো ওই
হ্যাঁ
সুতরাং ইট হ্যাজ টু বি অফ দ্য অর্ডার অফ দ্য ডাইমেনশন অফ দ্য পার্টিকেল। It
আচ্ছা
cannot, if it becomes very large, very মানে ওর থেকে যদি অনেক বড় হয়ে যায়, if it becomes too much bigger than the dimension of the particle, then the uncertainty becomes too much. Then it doesn't make sense to represent a particle by it, because we know that all material particles, no matter how small they are or how fast they are moving, they are actually very localized entities. Okay, so the wave packet, the size of the wave packet has the order of the dimension of the concerned particle, which is why it becomes logical to associate group of waves forming a wave packet. And also we showed mathematically that the velocity of the particle matches with the group velocity of such a group of waves that are moving along with the particle. So this is the qualitative discussion that gives you the logical background behind the simple mathematical calculation where we superposed just two waves. We superposed just two waves and we derived the expression of the group with the modulated amplitude, and we saw that the group is actually formed, the wave packets are actually formed, and they actually do move ahead with the velocity of the particle. Group velocity is the same as the velocity of the particle. And we also obtain the dimension, of course, which is a very approximate value because we considered only 2 such waves. Okay. Now we will be discussing the wave packet formed by the superposition of a number of plane waves, because that is what is actually happening in reality. It is not just two isolated waves, just as it cannot be one isolated wave. Similarly, it cannot be two isolated waves. We considered two isolated waves to make our lives simpler, because the simple mathematics itself gave us the result that we require. Okay, now we will move on to the more complicated mathematics, which of course we will not do in today's class. We will just discuss the background behind the superposition of n number of plane waves. Okay, so let's see. First of all, to obtain a wave packet which has a finite extent in space, superpose sinusoidal waves with, this is the sort of algorithm which will lead us to the formation of wave packets by n number of plane waves. This is the algorithm, but the mathematics will be done in the next class. So we superpose sinusoidal waves with a range of wavelengths within a certain interval delta lambda. Okay. Now such a wave packet will have a finite amplitude only within a range delta x, and the amplitude will be 0 elsewhere, just as we saw in the picture. The amplitude is finite over a certain extent. It is highest at the point where the particle is present probably, and lowest away from the particle. Okay. So if we consider combining infinite number of sinusoidal component waves, each with a wavelength within a prescribed interval delta lambda or reciprocal wavelength delta k, মানে সবারই যে ধরো আমি একটা ওয়েভ ধরছি উইথ ওয়েভলেন্থ ল্যামডা, তাহলে বাকি যে n মাইনাস ওয়েভ ওর সাথে যাচ্ছে তাদের ওয়েভলেন্থ গুলো কিন্তু সবারই ল্যামডা প্লাস ডেল্টা ল্যামডা বা ল্যামডা মাইনাস ডেল্টা ল্যামডা হবে না। ডেল্টা ল্যামডা একটা রেঞ্জ, ওই রেঞ্জের মধ্যে ওদের সবার ল্যামডা প্লাস মাইনাস ডেল্টা ল্যামডা, এই রেঞ্জে ওই সবকটা n খানা কম্পোনেন্ট ওয়েভের ওয়েভলেন্থ লাই করবে। দিস ইজ দ্য প্রেসক্রিপশন। ঠিক আছে? Now these component waves will be in phase within a very limited interval of space delta x, and beyond this they will fall out of phase. তাহলে ওই delta x distance টুকুর মধ্যেই they will be in phase and therefore produce the high amplitude. যেই তার বাইরে চলে যাবে they will fall out of phase and amplitude টা 0 হয়ে যাবে। আবার they will fall in phase and form the next packet. আবার they will fall out of phase and amplitude টা 0 হয়ে যাবে। তো বেসিক্যালি ওই যে মডুলেশনটা অ্যামপ্লিটিউডের হচ্ছে, that is governing this. Okay, that they will be in phase within a very limited region in space. So they will combine constructively, giving a high amplitude only within this interval. And once when proceeds further away from this region, the combination of phases become random so that they sum up to 0. So সেইখানে wave packet গুলো নেই, তারপরে আবার আসছে। তো এইভাবেই তো wave packetটা বা পালসটা propagate করছে। মানে পুরো জায়গাটাতেই যদি থাকতো তাহলে তো পুরোটাতেই আমরা ফর্ম অ্যামপ্লিটিউড পেতাম, সেটা তো কিছু জায়গায় পাচ্ছি কিছু জায়গায় পাচ্ছি না, সেইভাবেই মুভ করছে ওয়েভ প্যাকেট। Now larger the range of delta k, smaller will be the interval delta x, okay, and the length of the wave packet. So we want large number of waves to participate in this phenomenon. Larger the number of waves participating, more will be the range of the wavelength and smaller will be the interval delta x, okay, the length of the wave. So this mathematics that will be involved in this analysis. So this is the algorithm for Fourier transformation. Okay. So following this, we will see how using Fourier transformation we will get the required wave packet by summing up infinite number of plane waves. So we saw the simple case when two waves propagate and give us a wave packet, okay, but we have to remember that when a very few number of waves are propagating, the dimension of the wave packet becomes very large. So it is all right for doing that. So it is all right to do that mathematics in order to understand simply what is happening, but in order to actually get the real picture, we cannot avoid the summing up of failures. Okay? In fact, infinite number of failures, and that cannot be done just using trigonometry. For that, we have to take course of this algorithm that I have just set up, this qualitative analysis, and using this qualitative analysis as the background, we will do a particular kind of mathematics which is known as the Fourier transformation. Okay, but Fourier transformation would require certain in-depth discussion, which I don't want to pile with this class, because I want to start afresh with Fourier transformation. So in our next class, which is coming Wednesday, what we'll do is, what I plan to do is, given today's scenario, given today's scenario, okay. So if now up to this, I hope everything is clear to you. Okay, so I'll escape